All right, so this is lecture 20 or day 20 of probability. We're going to be doing a lot on the normal distribution today. I have deliberately not looked at my notes too much for this lecture because I want to try to do the algebra with a fresh perspective and not knowing what is the right and optimal way to go through the algebra. All right, so I may be accidentally or deliberately stumbling at times. I want you to be paying attention, trying to advise me on the best way to go. Okay. How many different names can you think of for the normal distribution? We have normal, Gaussian, bell curve. There's at least 3 names. Anything with this many names is probably important. Okay? So normal. So we'll say x is normal with mean mu and variance sigma squared if it has the density fx of x is 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. So sigma squared is the variance, mu is the mean. Technically, we have not proven yet that this is a probability distribution, and if it's a probability distribution, we haven't proved yet that mu is the mean and that sigma squared is the variance. However, given that we are writing it in this way, it is highly suggestive of all of those facts. So we'll first prove that it is a probability distribution. What are the 2 conditions we must check? Greater than or equal to 0. And the sum or the integral is 1. Okay? The non-negativity is easy. So is it a density? So 1, it is non-negative. That's not bad. So the next is we need to show that it integrates to 1. I'm going to do the special case mu equals 0 and sigma equals 1. You can reduce to this case by a change of variables. You should be comfortable enough in calculus to do that change of variables to reduce to that case. So I will leave the rest as an exercise. All right, so we want to show, let's let I equal the integral from minus infinity to infinity of 1 over the square root of 2 pi e to the negative x squared over 2 dx. We want to show that this equals 1. Okay? And as a nice calculus exercise, you can reduce the general case to this case. Has anybody seen the evaluation of this integral before? Okay, if you've seen it, you are not eligible to speak. The best way I know to evaluate this integral is through multivariable calculus. Now, when you're looking at this, why might multivariable calculus seem a silly way to go? There's only one variable. Okay? This really does not look like a multi-problem. So, English majors, how would I say the left-hand side? Is this I squared is or I squared am? All right. Minus infinity to infinity, 1 over square root of 2 pi e to the minus x squared over 2 dx, and then integral minus infinity to infinity, 1 over square root of 2 pi e to the minus y squared over 2 dy. I can't use the same letter twice. Or I could, but it's really dangerous and potentially misleading. So if I'm squaring I, I'm just writing the integral twice. This is the same as 1 over 2 pi, the square root's reinforced, the integral minus infinity to infinity, minus infinity to infinity, e to the negative x squared plus y squared dx dy. Now again, only for people who haven't seen this before, what does this suggest we do? Should be over 2, thank you. Not close. Not symmetrically, you need to have a z, so you're close. Polar. So in polar, we have x is our cosine theta, y is our sine theta, and then dx dy is r dr d theta. A better way of viewing that is it's dr times r d theta. Because now r d theta is going to be a length. D theta is not a length. Okay? So what we want to do now is we want to use polar coordinates and change. It does not want to move from this one. All right. So we want to use polar coordinates and evaluate this. Okay. The nice thing is whenever we have something like x squared plus y squared, this becomes just an r squared. And e to the minus r squared is a very tough thing to integrate unless we have an r down below, which we get with the polar change of variables. So again, in multivariable calculus, we have two things we can do. We can change variables, and we can switch orders of integration. Well, when your orders of integration are from minus infinity to infinity both times, switching the order of integration really doesn't help too much typically. All right, so now we get that I squared is 1 over 2 pi. The integral theta goes from 0 to 2 pi. The integral r goes from 0 to infinity. E to the negative r squared over 2 r dr d theta. The theta integral is very easy. What does the theta integral give us? So what do we get when we integrate theta from 0 to 2 pi? We just get 2 pi. There's no theta dependence in the integrand. So we just get a 2 pi. And then we have an integral from 0 to infinity of e to the minus r squared over 2 r dr. And it's amazing how beautiful things are. Because we have the 2 down below, when we take the derivative, we'd get a negative r. So when we take the antiderivative, it becomes very nice. We just get its e to the negative r squared over 2, and then we switch the order of the bounds because of the minus sign. So again, if you're not comfortable with this, just go through the integration slowly when we take the antiderivative. And now when we put in 0, we get 1. E to the negative infinity squared is just 0. And so we get 1. And so it is a probability distribution. Okay? You have to justify maybe converting to polar coordinates. The rapid decay allows you to justify this in a real analysis class. Or you can always take your huge circles getting larger and larger and larger and do some kind of limiting argument. Real analysis is not a prereq for this course, but whenever we have an improper integral, I just feel compelled to just say a few little caveats. Okay, any questions on how we evaluate this integral? We'll see later that this is related to a gamma function, and that's another nice way of interpreting what's going on. As we return, we've now shown it's a probability distribution. The next thing is to calculate the mean. Okay? So there's a couple of ways to do the mean. The first is, by definition, it's the expected value of x is the integral from minus infinity to infinity of x 1 over square root of 2 pi e to the negative x minus mu squared over 2 sigma squared dx. If you want to think about what's going on, here's mu, and our distribution is symmetric about mu. Yes?
Shouldn't there be a sigma?
There should be a sigma squared down here. Yes, thank you. So a distribution is symmetric about x equals mu. Mu should be the mean. Okay? There's a lot of ways of calculating this. My favorite way is to do nothing. Okay? What are the two ways we can do nothing? We can multiply by 1, and we can add 0. What do you think? Do you think this is a way to do nothing through addition or a way to do nothing through multiplication? So if you look, we've got an x minus mu. We want things to look like x minus mu. We can write x as x minus mu plus mu. So we've added 0. That's the big thing, is adding 0. And now we get that the expected value of x is going to be the expected value of x minus mu plus the expected value of mu. Or if you want to write it out the long way, it's the integral from minus infinity to infinity of x minus mu 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared dx plus the integral from minus infinity to infinity of mu 1 over square root of 2 pi sigma squared. There's a lot of writing today. E to the negative x minus mu squared over 2 sigma squared dx. This is the advantage of writing x as x minus mu plus mu. This integral is very easy to evaluate. This is a probability distribution, and I've just multiplied it by mu. The integral of a probability distribution is 1, so what is this piece going to be? It's going to just be mu. So the second piece is just mu. Let's look at the first piece. What's the integral of the first piece? So I claim you can get it without doing any integration by inspection. Yes?
Isn't it an odd?
It's an odd function. So this function over here, e to the negative x minus mu squared over 2 sigma squared, this is symmetric about the point x equals mu. This is an even function. We then multiply this even function by this odd function, x minus mu. X minus mu is odd about mu. So if I look at x as mu plus 5 or mu minus 5, they have opposite values. One of them would make this equal to 5, one of them would make this equal to minus 5. If you want, change variables. Let t equal x minus mu, and then you'd have the integral of t e to the negative t squared. You would have the integral of an odd function now symmetric about the origin. What's the integral of an odd function? 0. Now we have to be a little bit careful. When we had the Cauchy distribution, we had a little bit of a discussion as to whether or not the integral is 0. And in the end, we said that, well, for the Cauchy distribution, the integral of the absolute value does not converge. Therefore, we're not quite comfortable saying anything about that. But over here, we have such rapid decay that we're fine. This is where real analysis would save the day. And this integral will just be 0. So we get 0 plus mu, which is also known as mu. So it does prove that the mean is mu. Okay? The other thing we could do is to just make things a little bit easier, is we could always transform our variables. Instead of looking at the variable x, we could look at the variable maybe x minus mu over sigma. And that would transform things, see how that behaves, and then pass it out. So I want to just talk a little bit about that. So we could look at the, well, actually I guess I'll use the variable z. Let z be x minus mu over sigma. So we're translating, this is not a good camera day. Okay, good. So we're translating x by mu, and then we're dividing by sigma. And if we look at this new quantity, we can ask how things are related. And so if you calculate the expected value of z, it's going to be related to the expected value of x. We have very nice constants. You can calculate the variance. And so you get the expected value of z is equal to the expected value of x minus mu over sigma. And then the variance of z is going to be, now we have to use our rule, the variance of a multiple is that multiple squared times the variance. So we would get the variance of x over sigma squared. If we shift everything by a constant, does that change the variance? No. Variance is talking about how much things are fluctuating about the mean. If I shift all the scores by 2 billion, it changes their magnitude, but it does not change their fluctuation. If I change things from measuring things in meters to feet, then that will change the size of the fluctuations. Okay? So you can often pass from one variable to another. If we understand one, we understand the other. If I know the mean and the variance of x, I know the mean and the variance of z. Conversely, if I know the mean and the variance of z, I can get the mean and the variance of x. Okay? So it's often enough to say, let's just study the special case when mu equals 1, when mu equals 0 and sigma equals 1. Because if we can handle that case, we can unwind to the more general case. Okay. Now we want to calculate the variance. So the variance is a little bit more involved. And I'm going to do the special case when mu equals 0 just to make life simpler. All right? So I want to calculate the integral from minus infinity to infinity of x squared 1 over square root of 2 pi sigma squared, I keep dropping that today, e to the negative x squared over 2 sigma squared dx. Right? We need to do this integral. What is your least favorite technique of integration? Okay, so if you say integration by parts, I am going to have to ask you to leave this class. Yes? Partial fractions, you may stay. Okay, partial fractions is usually the one that's hated the most by people learning integration techniques. It turns out to be useful for a bunch of things. Integration by parts, we have to love that. Okay? Or at least if you don't love it, you have to be willing to use it repeatedly. It's one of the easiest techniques to use, and it works for a whole slew of things. So if we want to integrate by parts, we have to choose what we want for u and what we want for dv. What's the most natural guess to make for u? I don't care if it works. Yes?
X squared.
X squared, excellent. Horrible choice, by the way, but exactly what I wanted. Right? Why is this the right choice? Well, x squared is causing trouble. When we go from u to du, we're going to decrease the power of x, which is great. The problem is now our dv is, I'll pull that outside, is e to the minus x squared over 2 sigma squared dx. And we don't have a nice way to do the antiderivative. Right? So we're stuck. So unfortunately, this was the right thing to try, but it doesn't work. Okay, what else could we do? Yes, x. And then we put the other x over here. So we break up the x. Now when we take du, we just get dx. And because we have the x, we should actually put the x in front of the dx. And if we write it like that, this is now set up so that we can integrate. So what function has derivative e to the negative x squared over 2 sigma squared x dx? So e to the negative x squared over 2 sigma squared. And now when we take the derivative of this with respect to x, we get this back. We'll get a negative sign. All right, so if we have a negative sign, we've got to remember to put a negative sign over here. And then the derivative of this will give us a 2x over 2 sigma squared. The 2's cancel, so we'll have a 1 over sigma squared. So I think we need a sigma squared over here. Okay? And now when we'll now have x times dv. We'll have uv, which is x times this at plus and minus infinity. So it's uv at minus infinity, infinity, minus the integral of v du at minus infinity, infinity. So the uv term is going to be negative x sigma squared e to the negative x squared over 2 sigma squared. And I've got to divide by the square root of 2 pi sigma squared at minus infinity and infinity. And then I have a minus and a minus is a plus, which is great. So this is just integration by parts, plus an integral from minus infinity to infinity of v du. The minuses cancel. I have a sigma squared that comes outside. And I'll have a 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx. So now we have to figure out what's the first piece. Well, the e to the negative x squared goes to 0 much faster than x goes to infinity. If you're not sure about this, this is where you can use L'Hopital. All right, I think the camera is too far away today, so let's try moving it up a little bit. All right, so if you're not sure, you could do a L'Hopital. So you would have x over e to the x squared over 2 sigma squared. Take the limit as x goes to infinity. How do we use L'Hopital? If we have 0 over 0 or infinity over infinity, we just take the derivative of the top and the bottom until we no longer have 0 over 0. So this would become the limit as x goes to infinity of 1 over e to the x squared over 2 sigma squared. And now we would have to take the derivative of this, which would become x over 2 sigma squared. And we would see that as x goes to infinity, this is going to just go to 0. So by using L'Hopital, we're able to see that this piece over here is 0. Right? So the boundary term in the integration by parts is 0. And this is because of the extreme rapidity of decay. What about the second integral over here? Well, this is just our probability density. So we're just integrating our probability density, which is just 1. And so we get 1 times sigma squared, which is sigma squared. And so this is a way to prove that the variance is sigma squared as claimed. And again, it's just integration by parts. It's a good idea if you're not comfortable with this to just go through the integration very slowly and see what's needed. Okay. So the point of all this is that our notation is justified. Whenever you see mu as a parameter, that should be the mean of your density. Whenever you see sigma squared as a parameter, that should be the variance. If that's not the case, it's bad notation. If you look at the notation for an exponential random variable, we actually use lambda as our parameter. And this allows us to have crazy people who have their exponential distribution defined the wrong way, with the reciprocal of the correct value, because we're not using the letter mu. Anybody have any other ways we could calculate the variance? How else could we calculate the variance? What other technique might we be able to use? What technique have we used to calculate means and variances? Differentiating identities. So, variance by differentiating identities. Right? I'm only going to consider the special case mu equals 0. Why? Well, if I can do the case mu equals 0, I can do the general case. Mu is not going to change the variance. So let's say x is normal with mean 0, variance sigma squared. Now what's interesting is if you want to calculate the variance of the standard normal has sigma squared equals 1. The best way to do that with differentiating identities is to consider the whole family of normal distributions with density depending on sigma squared. And then at the end of the day, specialize sigma squared to be 1. Because if you're doing differentiating identities, you have to have some parameter that's varying. So even if we only care about the standard normal, we have to look at a whole family of densities. Okay, so what we want to do is we want to calculate the variance. So the variance of x would be the integral from minus infinity to infinity of x squared e to the 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx. Now we need to start with an identity. What's the identity we know in this case? So what identity do we know? The density function. The density function integrates to 1. So we know the integral from minus infinity to infinity of 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx equals 1. Or if we multiply through by sigma, we would get the integral from minus infinity to infinity 1 over square root of 2 pi e to the negative x squared over 2 sigma squared dx equals sigma. And now this is set up to use differentiating identities. What class do we need to justify interchanging the integral and the derivative? Real analysis, right? 90% of the time, real analysis is the solution. All right, so we assume now we have taken a real analysis class, or we trust somebody who's taken a real analysis class who tells us that the conditions are met and you can interchange the integral and the sum, the integral and the derivative. And so now we take d by d sigma, and that's going to give us the following. On this side, we'll get the integral from minus infinity to infinity 1 over square root of 2 pi e to the negative x squared over 2 sigma squared. And now when we take the derivative of that, we're taking the derivative with respect to sigma. So what comes out? It'll be negative x squared over 2, where the sigma to the minus 2 becomes a sigma to the minus 3. And we would have a negative 2 come out. So the negative signs cancel. Think of it as you have a sigma to the negative 2, so a negative 2 sigma to the negative 3 comes out. The negatives reinforce, the 2's cancel. And what should that equal? Well, if we're taking the derivative with respect to sigma, it just equals 1. Okay? So now let's look and see what's going on this side. The 2's cancel, which is nice. We have an x squared, which is looking a lot like what we want. What do we want to have down here? Square root of, I'm sorry?
We want a square root of 2 pi sigma.
We want a square root of 2 pi sigma squared. So we want to take a sigma from the sigma cubed and move it into the square root of 2 pi. And then we'll have an extra 1 over sigma squared. What do we do with that extra 1 over sigma squared? Move it over. And so this gives us the integral from minus infinity to infinity of x squared 1 over the square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx equals sigma squared. And here's the answer. We now have two methods we've done today to calculate the variance. One is integrating by parts. One is differentiating identities. Which do you prefer? This is in some sense personal preference. I prefer the differentiating identities. If you want to calculate higher moments, if you want to calculate x to the 4th, x to the 6th, x to the 8th, you can keep doing that. I don't have to worry about the odd moments of the standard normal. All the odd moments will vanish. One of the best ways to actually calculate the higher moments is by induction. And you can do this either by differentiating identities, or you can do it by integrating by parts. Is if I know the 2nth moment, if I want to calculate the 2n plus second moment, I will reduce it to something nice times the 2nth moment. And here's a beautiful fact. The expected value of x to the 2m is 2m minus 1 double factorial. We've seen that number before earlier in the semester. Does anybody remember where we saw 2m minus 1 double factorial? Yeah, when we're picking objects. So if we have 2m objects and we care about how many ways can we split them into m pairs, where we care who your partner is, but we don't care if you're the first pair, second pair, third pair. The answer was 2m minus 1 double factorial. Those are the moments of the standard normal. What this tells us is there's actually some combinatorial significance hidden or built into the Gaussian. And towards the end of the semester, I like to save the last week to do applications of probability. It's a way for me to talk about some of the research I've done with students in the small program over the years, and I will talk potentially about random matrix theory, where stuff like this comes into play. Okay? So there's a lot of stuff we can do now. Okay? Is everybody comfortable on this part? Okay? Now the fun begins. All right, now we have normals. Okay? What we want to do now is we want to look at sums of normal random variables. And there's lots of different ways we could do this. So let's say xi is normal with mean mu I and variance sigma I squared, and they're all independent. And we can look at x1 plus xn. And we can ask, what is the distribution of this sum? So I have a bunch of normal random variables and I add them. How many of you are either stats majors or potential stats majors? Okay, so this is something you might see in terms of trying to do error analysis, where you often have a lot of Gaussian errors, and you want to know how that sum is distributed. Okay? There's a beautiful answer. What's the first thing you should do when you see a distribution? It's not a rude question. Yes? Find its mean. The first question you should ask is, what is your mean? Right? And what's the second question? What's your variance? So let's call this x. So the expected value of x, we have linearity of expectation. The expected value of a sum is the sum of the expected values. So this is going to be the sum, k equals 1 to n, of the expected value of xk. So it's just mu1 plus mu(n). So the expected value of a sum is the sum of the expected values. The variance is a little bit harder. So the variance of x is equal to the sum of the variances if they're independent. And since we're assuming they're all independent, the variance of the sum is the sum of the variances. In general, you have to worry about the covariance term. But if things are independent, we don't have to worry about that. So this is just the sum, k goes from 1 to n, of the variance of xk, which is sigma 1 squared plus sigma n squared. So we know the mean, we know the variance. Okay? Any thoughts as to what the answer might be? Any guesses? What might be a guess for the sum of normals? Yes.
Normal?
Yes. If you could make math the way you want, the sum of normals is normal. We call it, the central limit theorem. That sums converge to normals. Well, if sums are supposed to be converging to normals, what should sums of normals be? Should be normal. If it's converging to normal, well, sums of normals, I start normal and then I somehow get away from normal and converge back to normal, that seems silly. So just because you know the existence of the central limit theorem, it is highly suggestive that sums of normals should be normal. We call a distribution whose shape is unchanged under adding independent copies stable. So the normal distribution is a stable distribution. So sums of normals turns out to be normal. Another distribution is stable, and it's a very strange distribution. Any thoughts as to what this distribution is? Very few distributions have shape unchanged. Is there? Yes?
A binomial?
Not a...
Is the probability of success the same?
Yeah, binomial plus binomial would be binomial. Yes. But I said strange, so you're wrong because I said strange. We're not going to call the binomial a strange distribution. Yes? Yeah, the Cauchy. The Cauchy is actually a stable distribution. And there is a way to have the normal and the Cauchy in a family together and interpolate from one to the other. So who are the econ people in this class, or at least willing to admit that they're econ? Okay, so there's a lot of good mathematics and bad mathematics used to model things like the stock market. And sometimes people use the random walk hypothesis where you flip coins and the coin might be biased, hopefully positive, for the stocks to be going upward. There's also approaches using fractal geometry. And this is where Mandelbrot has some great stuff. I'll put some links to this in the additional comments. And what Mandelbrot and other people say is that these random walk models do not have enough days of high deviations, of high movements. Something like the Cauchy distribution will allow you to have more of those days. And what's interesting is both the Cauchy and the normal are stable distributions. Anybody know any other distribution that's stable? Yes? Which one? I'm not sure about that one.
I thought those were supposed to be more representative of stock market returns.
Okay, send me an email so I can check on that. The one I was thinking of was the Levy distribution. I think is also normal, is also stable, but I'm not 100% sure on that. There are not that many of them. Typically, when you add copies, your shape changes. So how would we prove? So let's conjecture x1 plus xn is normal. Well, if it's normal, there's only one normal it could be. it must be normal mu1 plus mu n sigma 1 squared plus sigma n squared. Because we already know the variance and we already know the mean. Right? So if it's going to be a normal, it has to be this one. Now we need to show that it's this one. Is there anybody who's really excited about calculating the sum of n independent random variables all at once? How should we do it? Yes? Induction. We can do it 2 at a time. So think about this. Let's say we have x1 plus x2 plus x3 plus x4. If we show x1 plus x2 is normal, now this is normal plus normal. And if we've already shown the sum of two normals is normal, what's normal plus normal? Normal. Now we'll look at this, and we now know that the sum of those three is normal. What's normal plus normal? Normal. So it's enough to do it just 2 at a time. Okay? So there's a lot of different ways, and I go through a bunch of them in the book as to how we would prove that sums of normal is normal. So this is where the algebra can get very intense. Now, one of the advantages we have is we have a belief that it's supposed to be normal. So this can guide us in how we're doing the algebra. We want to do things in such a way that we are able to get a normal distribution at the end. All right. Let's see, I don't think we need this anymore. We understand what the means are. We understand what the variance is. And we're only going to do the special case of 2. Okay? Are there any simplifications we can really do? Can I assume the two means are both 0? Is that bad? Because all the means does is it just picks up everything. The standard deviations, that might be a little bit harder to justify. I can take both standard deviations to be 1. Because in fact, when I'm adding over here, I'm not going to get the same standard deviation coming out. These will not all have the same standard deviation. I don't want to do some kind of shift like that. But I can always shift them to have mean 0. That's just going to shift the whole sum by the sum of the means. So to make the algebra a little bit simpler, I'm claiming I can assume the means is 0. If you wanted to, by all means, we could kill more chalk, we could fill more pages, we could keep the means general throughout the whole analysis. It's just going to make it harder to follow what's going on. So it's worthwhile to spend a few moments and see what kind of algebraic simplifications can we do. Okay? So we can, without loss of generality, mu1 equals mu2 equals 0, show x1 plus x2 is normal 0 sigma 1 squared plus sigma 2 squared. That's what we want to do. And if we can do that, we're done. And then the rest follows by grouping. So grouping is one of my favorite proof techniques. Essentially, if you can do something once, you can just keep grouping and expand it outward, as long as we're only doing it finitely many times. All right, so now we want to calculate x1 plus x2 and calculate what is its distribution. Okay? So there's lots of ways to go. I mentioned very briefly at the end of last class the convolution. Right? So let's let x be x1 plus x2. So you could do the probability that big X is less than or equal to little x. And this is going to be the cumulative distribution function of x. This is a nice way to review. So we would have x1 goes from minus infinity to infinity. x2 goes from minus infinity to x minus x1. And we would have f of x1 of x1, f of x2 of x2, dx2, dx1. So this is the probability that the sum of these two values is at most little x. Because if x1 takes on the value, if the first takes on the value of x1, the second can go all the way up to x minus x1. We then calculated the density, which was taking the derivative, And so when the dust settled, we had x1 goes from minus infinity to infinity, f x1 of x1, and then f x2 of x minus x1 dx1. And sometimes we like to use a different variable. We sometimes like to use the variable t. So often t instead of x1. Right? So this is my density. What do I need to show for this density? What do I need to show this density equals? What must this density equal? What's my goal? I want to show it's the normal with mean 0 and variance sigma 1 squared plus sigma 2 squared. So the goal is show fx of x is some constant c e to the negative x squared over 2 sigma 1 squared plus sigma 2 squared. I have a lot of favorite techniques. This is another one of my favorite techniques. This is the theory of the normalization constant. This is a probability distribution. If you integrate this, x goes from minus infinity to infinity. If I integrate this over x, little x, well, I can integrate this first. And if I integrate this over little x, I get 1. And then when I do this integral over x1, I would get 1. This is a probability distribution. The integrand is non-negative, so it's clearly going to be non-negative. It is a probability distribution. It integrates to 1. Imagine I know that it has the correct functional form of x, but maybe it doesn't have the right normalization constant. Well, since it has to integrate to 1, this normalization constant would then have to be 1 over the square root of 2 pi sigma 1 squared plus sigma 2 squared. It would have to correct and improve itself. So that's what's wonderful about the theory of normalizing constants. I don't have to get the answer exactly right. I just have to sniff out the functional form in little x. And if I can do that, we win. Okay, we've got a little bit over 5 minutes left. Let's wish ourselves luck. Okay, so fx of x is equal to the integral from minus infinity to infinity. I'm going to use the variable t. So the first one is I'm now replacing my density at t. So I'm going to get a 1 over square root of 2 pi sigma 1 squared e to the negative t over 2 sigma 1 squared. And the next one is 1 over square root of 2 pi sigma 2 squared e to the negative x minus t squared over 2 sigma 2 squared dt. Okay? Does everyone agree that this is what we get when we move things? No, okay, I've made an algebra mistake. Ah, yes, it should be t squared over here. Thank you. Okay. So I want to get things in terms of x. Okay, so what I can do is I have some constant. All right. I'm not going to bother writing what it is. It's 1 over the square root of 2 pi sigma 1 squared, 1 over the square root of 2 pi sigma 2 squared. Okay? Are people happy with me, fine with me just writing c? So I have this, the integral minus infinity to infinity e to the negative. And now let's see what we have. We have x minus t squared over 2 sigma 2 squared plus t squared over 2 sigma 1 squared dt. And we need to do this integral with respect to t. Okay? So, this does not look exactly like an integral we need to do. And since there's still 5 minutes of class, I can't just say read it in the book. So we're going to have to go through and do this. Okay? We always want to reduce things to things we've seen before. Okay? this looks like some kind of polynomial in t. So let's actually just investigate the exponent. So the exponent, we're going to have, if we expand this out, we'll have a t squared over 2 sigma 1 squared plus a t squared over 2 sigma 2 squared, right? And then when we keep expanding this, I'm not really worrying about the minus sign over there. Then we'll have a minus 2x over 2 sigma 2 squared t plus an x squared over 2 sigma 2 squared. Right? If we can write this as t minus something squared, or some constant times t minus something squared, we can actually evaluate that integral. This x has no t dependence, so this is fine. So if we want to look at this, we want to complete the square. So we have 1 over 2 sigma 1 squared plus sigma 2 squared, t squared minus, okay, so now we've got to figure out what we want this piece to be. I'm pulling out a, oh wait, this was bad algebra, right? It's 1 over 2 sigma 1 squared plus 1 over 2 sigma 2 squared. So I get a t squared minus, I multiply by 1 over 1, so I would get a 1 over 2 sigma 2 squared over 1 over 2 sigma 1 squared plus 1 over 2 sigma 2 squared xt, right? Because now if I multiply this through, I just get exactly the term I had. Now what do you think I want to do? What do you think we want to do at this point? So we've got t squared minus something xt. Yes?
You're going to want to add 0.
I'm going to want to add 0.
X squared.
Right, so it's going to be something times x squared. And if we do that, we're going to complete the square. So now we want to add something times x squared. So we want to basically have what? So we've got to think, we want to be able to write this as x minus something. This term here is supposed to be twice the first times the last. So I would essentially need, I think, like a square root of this. And then when I'll square it, so I think it's just 1 over 2 sigma 2 squared, 1 over 2 sigma 1 squared plus 1 over 2 sigma 2 squared x squared. And then I think I want 1/4 and I think I want this squared like this. Because now, when I look at what I have here, I can write this all as 1/2 this times x. When I multiply by t, and I take 2, it's going to cancel. And so now I then have to add this back. So I'll have, so since I added this, I now have to subtract it. So I would then have 1 over 4, 1 over 2 sigma 2 squared, 1 over 2 sigma 1 squared plus 1 over 2 sigma 2 squared. And now I multiply by 1 over sigma 1 squared plus 1 over sigma 2 squared. So this was originally squared, so this one is no longer squared. I think this one is still squared with an x squared. So you can check the algebra, but it should look something like this. Okay? quite possible I made a small algebra mistake on the board. But now let's look and see what we have. This part over here, it's going to be an e to the negative t minus something squared. And when we do that integral, it's going to just be a nice number. And then this part over here has no t dependence. We can just pull this out. And so when you take this and add this part over here, it should at the end of the day come back and give us exactly what this is. And then there'll be a c floating outside from doing the t integral and from having the c over here. So when you put this in, this will look like some constant times t minus something squared. And we know how to integrate that. It's essentially a shifted normal. Okay? So this is just a way to see what the calculation is. So I strongly urge you to go home and read the book. It goes through an excruciating detail of what's going on. All it really is it's completing the square and noticing that this part becomes an integral that just gives us a number. And then the remaining part has the x dependence. And when you do all the algebraic bookkeeping, the x dependence you get is exactly what you want. Okay, so this is a good place to stop on the algebra of the normal.